Hello everyone, thank you for coming. Welcome to the talk. My name is Waleed AlZamil and this is Bandar.
My name is Bandar Alharbi, and for the agenda of this talk, we will do LPC and we talk about our goal, then we'll talk about the LPC security mechanism. Then we will analyze and investigate the result of the LPC. After that, we'll give you an introduction about protection. We'll go through a little bit of some techniques and examples. Lastly, we will talk about the attack and so we have used the LPC-1343. It is part of the LPC microcontroller family. We have used the Olymix board, the one shown in the corner. It's a Cortex M3 based. And it's hardware architecture, which has 3 dedicated bus, one for the instruction, one for the data, and one for the peripheral. The LPC considered to be a low power consumption microcontroller, and it's easily integrated with other embedded systems. Some of the previous work that done on the LPC by Chris Mileski, we will go into it and talk about it in the coming slides. So our main goal is to try to study the LPC debug locking mechanism. Then we will try to targeting to re-enable the debug interface in the earliest stage. The LPC series, they have something called code read protection, CRP. CRP is the convention name of the NXP. Some other vendors have their own convention names such as RPD and security instances. They have 3 levels of read protection, CRP 1, 2, and 3. All of them will disable the JTAG, and each of them will have a dedicated value. The main difference between them is related to the ISP commands restriction. The ISP is a serial protocol to access the memory, access the LPC to do some operations such as read, write, and raise. So the user easily just, if you want to configure the CRP, just by writing the CRP value to a specific address in internal cache, and it will trigger the CRP to disable the JTAG. And for the LPC-13 series, the address is the 0x to FC. And in this table, we can see whenever the CRP is set, the JTAG will be disabled. And here we have the LPC-13 series memory map, and we will try to point to the main interesting addresses. The first one in the below, the red rectangle, is going to where the 0x to FC exists. The second one is in the blue area, which have the blue front port, which can be easily done with the space. And the third one is on the right side, which points to the system control register, which is not fully documented register, but we think it's used to disable and enable the JTAG. And here we have the boot process. We have 2 areas where the CRP will be checked. The first one is in the green area, which will be targeted. It is just simply reading the content of 0x to FC, and based on the content, compare it with the CRP levels. In case of any matching, it will disable the JTAG. In other cases, it will just. And the red area where the ISP commands restriction happen, and there is where Chris and others did their work. It's good to know that this piece of code it will read the content of 0x to FC from the internal flash again to do the ISP commands. After we dump the boot ROM, we load it with Hydra, and we have used the SPD loader, level down security, which is really helpful plugin that makes reversing most of the microcontroller easier by basically mapping the memory map control to the Hydra. So we did reverse this part of boot process. As you see at the beginning, it will load the needed value and prepare the register. Then it will load the content of 0x to FC to R4 register. And based on that content, we have a three main scenario of execution. Let's start with the CRP3. In case of the content of 0x to FC equal the CRP3, it will first compare with R5, which contains the CRP3 value, and it will branch to the load CRP2 level. And there it will load the CRP2 to R4 register, as you can see here. And after that, it will store the R4 register to the system control register to disable the JTAG. In case of the content is equal to the CRP1, it will follow the black arrow. As you can see, in the middle, there will be check to compare it with R6, which contains the CRP1. And in case of equal the CRP1, it will continue to execute to load the CRP2 level. And here, it will again load the CRP2 R4 register. Then the R4 register will be stored to the system control register to disable JTAG. And so again, the CRP2 value is used here. And other cases, including CRP2, it will follow the blue arrow. And it will branch before loading the CRP2. And store the content of R4 register to the system control register. In case of the content of R4 register is equal to the CRP2, it will disable the JTAG. In other cases, it will enable the JTAG. So we can notice there is like a magic value to disable the JTAG, which is CRP2 for all CRPs. Okay, in this slide, we try to abstract the boot process for master system. It's usually we start from the initialized component to load the configuration from non-volatile memory. Some will say use memory, but then it will execute the logic mechanism based on the chip. So we have an attack window while we loading the configuration from memory. Somehow we can have the configuration value or have the register that contain the value or bypass the important instruction. And as you can see in the execute locking mechanism, most of the LPC have a well-known design flow regarding the CRP configuration. You can see it's a 32-bit register where only 3 values is used to disable the JTAG, while the rest value will enable it. So we have much chances to re-enable it.
Hello again. In this slide and upcoming slides are a brief of what is fault injection, techniques, and some examples. So fault injection is basically hardware corruption during execution on a normal device. This hardware corruption could cause undefined behavior, and sometimes it's a bit flip, skip instruction, or even change in the instruction. The interesting thing is sometimes even though if you execute the same exact glitch again, the causes may differ, especially in the case of voltage glitching and clock glitching, and it becomes more accurate with advanced techniques. Speaking of techniques, we have clock glitching. As you know, every CPU contains a clock. Clock is known to be steady, so messing with the clock signal could lead to a glitch, and it's considered to be an easy, low cost, and doesn't require high skills if the device is using external clock. Also, voltage glitching is a technique. Voltage glitching is simply by tampering the supply voltage. For example, pulling down the right amount of voltage with the right amount of time could lead to a glitch. And our talk is based on this technique. Another technique is electromagnetic glitching, or EM. Basically, it's a strong EM pulse to cause a fault. Usually, the EM pulse is generated by a coil of wire, which will generate a strong current and cause a fault. This technique usually considered to be a higher cost than voltage glitching. Also, good understanding is needed to be able to get a successful glitch. Another technique, and considered to be an advanced technique, which is laser glitching. laser glitching happen by applying strong pulse, laser pulse, to a decapsulated IC. This kind of attack requires high expertise and expensive tools, however, has a high accuracy results. And also we have other techniques such as body Bison injection, temperature, and etc. Is it difficult? Well, it depends. Several years ago, Rescue released CTF challenges, and there were a specific challenge called Fiesta, which is based on a fault injection. One way to solve this challenge is only using a jumper wire. You could short the external clock terminals with the jumper wire to mess with the clock signal and cause a glitch to solve the challenge. And also it could be more complex with decapsulation and the double or even triple laser beams or pulses. Examples. We have the famous AirTag attack. Stack smashing managed to voltage glitch the AirTag and the firmware. To know more, don't miss last year's talk here in hardwear.io called Over the AirTag. Also, we have another example, bypassing Android MDM using electromagnetic fault injection, and the tool was a gas lighter. And also here is the famous Bitcoin wallet. Several people mentioned below. They were able to extract the PIN number of the wallet by applying voltage or electromagnetic glitching. Now we took a brief. Let's move on to our attack. In Recon 2017 talk by Chris Grensky, he was able to bypass the ISP bootloader security feature on NXP LPC by applying voltage fault injection to access the flash memory. This talk inspired us to go further and look for a vulnerability that will leverage re-enabling the debug interface and have full control of the microcontroller. And I can hear the LPC saying, I'm ready to get hurt again. As you can see here, this is our actual setup. The LPC 1343 on the left. The power and the glitch comes from the chip whisperer, which is the device on the right. And on the top, we have the debug probe connected to the LPC to check whether the debug interface is open or not. We also use the PCB byte where the glitch will come through and called it the poison needle. PCB byte is from SynSpeak company and help us to solder this. Also, we removed the decoupling capacitor on the V-core to make our glitch more convenient, as shown in the schematic on the right. Here's the setup diagram setup. The PC was connected to both the debug probe and chip whisperer. Chip whisperer is a powerful open source hardware from UA technology for side channel power analysis and glitching.
So from the boot ROM analysis, we have had three main scenarios: execution based on the 0x12C, and as you can see here, we took two power traces from the LPC-33. The yellow trace is point where the LPC put up to no CRB, and blue trace where the CRB when it's set. And you can see in the middle there's a little bit shift in the pink trace, and we will see the CRB1 will execute a different scenario than this. And here we overlap the two traces, so the shift became more obvious, and we found the sweet spot that will be targeted, which is around 159%.
So now we have the right range to apply the glitch. The setup was ready. Wrote the code to start glitching. Our trigger was based on a reset pin. So we are resetting the device, wait until the range, glitch, and so on. However, with no luck. Then we decided to change the setup and base the trigger on a power on cycle. So we power on the device, wait until the range, glitch, and power off, and so on. After a while, we successfully were able to unlock the debug interface. Why was it successful when we changed the setup? Remember this diagram? The boot process on reset was misleading. because it's shown in the green rectangle that after each reset, it will check the debug interface. Therefore, our initial setup was based on this diagram. However, when we changed the setup based on a power on-off cycle, the glitch succeeded and able to unlock the debug interface. And now with the recovery tool.
So we here have the boot process. We have here the boot the border trace captured from the LPC 1343 microcontroller. We configure it to CRP3. You can see after each glitch we check in the window if the bootloader is enabled or not. Eventually we succeeded to re-enable the debug interface in the early stage, and we connect to the debug interface, the G-Link. We'll try to access the LPC-1343 microcontroller, and we try to read the content of 0x to FC. It contains the CRP3 value.
And this is a trace screenshot from glitching CRP1 with no CRP, CRP2 glitch, no CRP, and all of them combined. This is a proof that we were able to glitch all CRP values and able to unlock the debug interface.
Let's talk a little bit about history. Before 2006, LPC microcontroller was part of Philips. At Philips' time, they developed the LPC-214 series microcontroller, which had a CRP mechanism. So we searched for documents from Philips, NXP, the same microcontroller, to compare the boot process, the code read extension, and we found it. Here is the boot process. As you can see, it's almost the same, but the NXP introduced CRP levels. And from the boot, from the code read protection, it seems the magic value used is the same as the CRP. For the LPC family, so based on the user manuals, we looked to all the LPC microcontroller and the following list sharing the same CRP mechanism and the boot process. So we assume it might be having the same vulnerability. And in the following points, the NXP changed the boot process and the locking mechanism. So there is introduced something called ECRP, which stands for Enhanced Code Read Protection, in the LPC-546 series, which has different approach to enable the JTAG by setting two specific for enabling the JTAG. And after that, they introduced something called OTP banks, the LPC-540 series that Google investigated. And the last one is the LPC-55 series, which is context-free based, which has different approach locking mechanism that we didn't investigate.
So, to conclude, we reversed engineered the boot ROM and took power consumption traces, and with comparing, we figured out the range that we should apply the glitch. We applied the glitch based on a reset trigger, but with no luck, changed the setup to base our trigger on a power on cycle. Then we were able to successfully re-enable the debug interface and have full control of the microcontroller. Another thing to mention is the CRP locking mechanism exists since Philips' time. We also contacted NXP to disclose. They were very professional and fast. Thanked us for highlighting the misleading step on the boot process diagram. And hope you learned something or two, and thank you for listening.
All right. Thanks, Waleed and Bandar. We have some time for questions. Do we have some questions from the audience? Yes, we do. Super.
Might have missed it, but I don't think you said how you actually got the dump for the boot ROM. Was it just unprotected and you could just read it out of memory, or was anything special?
Actually, it's just connect the debug interface using T-Link, and just give that address and load it to your PC. Then you can analyze it.
Do we have any other questions? Okay, I've got one. You mentioned in the end that you contacted NXP to disclose this problem. They fixed the documentation, obviously, but what else did they do?
I'm not sure they fixed the documentation already because we discussed it 2 months ago, and to be able to mitigate this kind of attacks, you should do a redesign, silicon redesign, or change the RAM to be able to solve this issue.
Did they inform you that they plan to do some mitigations, to introduce some mitigations to this problem, or didn't?
No, they didn't mention anything out there.
Thank you. Do we have any other questions from the audience? Super. I've got one.
Hi guys, thanks for your presentation. It's fantastic. Just a simple question. So you changed the trigger from a reset trigger to power on. Was it just time that you used as the basis for actually when you did the trigger? The reason I asked this question is I have exploited the ear tag glitch before, and what I found was I actually used the oscilloscope to trigger on just before the sort of dip, and that made it way more accurate. So I'm wondering if you was it just purely on power on at time, or was there any other sort of things used to target the watch time?
No, actually we used only power and time to able to do it.
All right. Last question? No one. Super. So let's give another round of applause to the guys.